world increasingly affected by anthropogenic climate change, we frequently discuss sea ice flux as both a result and indicator of a changing climate. For example, this graph displays an overall drastically decreasing trend in Arctic sea ice since 1979. However, we also know that the Earth has always undergone global patterns of warming and cooling. Paleoclimatology is a field of study that attempts to reconstruct past climates to help us better understand these patterns. My project specifically focuses on using a species of clam to reconstruct the climate of the Bering Sea several thousand years ago, which will help contextualize the effect of human climate change on sea ice today. I'm specifically looking at a time period referred to as the Neoglacial, which was a major cooling period that occurred 4,000 years ago during the mid-Holocene. The Holocene is our current geological epoch, and it began 12,000 years ago with a major increase in global temperatures. This graph shows the overall temperature shifts of the Holocene. Right after the Holocene climate optimum, a period in which the Bering Sea was hotter than it is today, the Neoglacial period began, and temperatures began to rapidly drop across the globe. Now, researchers are questioning if this temperature change was so extreme that it caused seasonal sea ice to extend as far south as the Aleutian Islands. This is Unalaska Island, a member of the Aleutian chain at the southern tip of the Bering Sea between Alaska and Russia. Sea ice has never historically been found here, but in the early 2000s, researchers discovered the bones of several ice-dependent animal species, including beluga whales, polar bears, ringed seals, and several other species, all dating back to the Neoglacial. As I mentioned, the Aleutians prior to the Neoglacial were even hotter than they are today, so sea ice suddenly extending this far south would have been a truly shocking environmental change. As Catherine West, an archaeologist studying Unalaska, puts it, it would be like Boston Harbor freezing over and polar bears appearing on our landscape. With that in mind, the guiding research question behind my project is whether seasonal sea ice did or did not reach Unalaska during the Neoglacial period. Crockford, one of the researchers who discovered those initial animal bones, argues that the presence of juvenile members of the species provides incontrovertible evidence that seasonal sea ice must have extended to the Aleutians. The arrow on this map indicates her proposed extent of seasonal sea ice. However, the extremity of this climactic change necessitates multiple different kinds of evidence to ensure that these bones were found on Unalaska due to sea ice and not for some other reason. So where does Saxidomus gigantea, or the butter clam, fit into this question? First, these clams are convenient. They are abundantly found both today and at archaeological sites. The image on this slide displays an example of a living clam found on Unalaska Island. Our archaeological samples are from several preserved shell middens in sites across Unalaska Island, which are displayed in the map on the right. These sites are of different ages from the early to late Neoglacial period, and the samples were collected by the Museum of the Aleutians. We are using them with the permission of the museum's owners and a local indigenous group called the Anangans. Also, this species is well suited to the study of sclerochronology. Similar to dendrochronology, sclerochronology studies the periodic changes in growth and chemistry in hard tissues of organisms like clams. Saxidomus specifically forms tidal growth increments that cease below 5 to 6 degrees Celsius, creating winter growth cessation bands. This pattern of growth, which researchers agree is primarily based on temperature, allows us to compare the growing season of ancient and modern clams. This is an image of a prepared sample of a Saxidomus specimen. The black arrows indicate several examples of winter growth cessation bands, and the white arrow indicates the length of a growing season between two bands. For this project, sample preparation is a vital part of making the data actually visible and useful. We begin by cutting millimeter-thick sections from each clam, often taking multiple. Then we polish these sections and typically stain them with something called mut-vi solution. This staining is a particularly lengthy part of the process, but as you can see in this image comparing the same section of a clam stained and non-stained, the tidal growth increments and winter growth cessation bands are much more distinct from the rest of the shell in the stained sample. We finish this process by using a digital microscope to take high-resolution images of our samples. To begin actually collecting our data, we first visually identify those winter growth cessation bands on the samples. Then we use a tool called a digital caliper to measure the distance between the first and second winter growth cessation bands. This is the most stable year of growth for the clam. In every other year of growth rate is much more irregular and tends to slow with age. While these winter growth cessation bands are typically quite easy to visually identify, other factors such as predation in ancient samples indicates the feasibility of sea ice during the period around Unalaska. If there was seasonal sea ice here at that time, we would expect to see significantly shorter growing seasons from the ancient clams as opposed to their modern counterparts. Also, comparing growth season lengths across sample sites of different latitudes allows us to gain more insight into how far south sea ice may have extended. To understand the results on this slide, it's first necessary to note that I'm still collecting data from more samples and that these trends are likely to shift. That being said, this graph displays the length between winter growth cessation bands of samples from our 3 archaeological sites and 1 modern group. These groups are ordered left to right, oldest to modern, and you can see the geographic position of all of our sites on the map on the right. Based on this initial set of samples, growth conditions were actually the most optimal at Margaret Bay, which is our earliest site dated back to the early neoglacial period. Also, the other 2 archaeological groups are not substantially shorter in growing season than our modern group on the far right of the graph. Altogether, this suggests that we may actually need to question the hypothesis that seasonal sea ice reached this area. However, future research is necessary to determine whether these visually longer growing seasons were actually caused by warmer temperatures as opposed to another explanation. So to reiterate, our growth season measurements provide general insight into the neoglacial seasonality of Unalaska, as temperature is the most important factor determining the growth of these clams. However, different nutritional conditions can cause a clam to appear to have a visually longer growing season while actually having grown for the same amount of time as a clam with a visually shorter growing season. This is because an environment with better nutrition allows the clam to grow more each day, widening what I was referring to as its tidal growth increments. This widening then makes the length between its winter growth cessation bands longer, causing it to appear to have a longer growing season while actually having grown for the same amount of days. We can correct for this possibility by actually going through and counting those tidal growth increments, verifying the number of tides that the clam is experiencing. This graphic displays how the clam's growth pattern displays incredible tidal regularity, allowing us to very directly link growth increments with specific time passage. Our next steps are to continue gathering data and to figure out how to optimize this process to secure the most accurate answer to the question of sea ice in Unalaska during the neoglacial period. Thank you all for listening, and I would love to answer any questions now.
I was wondering, why does this species of clam form winter growth cessation bands, and why do those bands appear visually different to other sections of the shell?
At around 5 to 6 degrees Celsius, it becomes metabolically inefficient for the clam to continue growing. So every so often, the clam kind of comes out of its shell to check the temperature and nutritional contents of the water, and then it recedes, which creates those thick winter growth cessation bands, which consist of a greater amount of protein than the rest of the shell during regular temperatures.
What are other potential explanations for the presence of ice-dependent animal species bones?
One hypothesis is that hunters were actually bringing back entire carcasses of animals like seals experiencing a greater amount of tides and days. But in a better growing season, those tidal growth increments will be wider because the clam will be taking up more nutrition each day.